In the last video, we have seen how we can import modules from other packages, such as the directory package, to have more functions available that deal with file system access, or from the random package to have functions available that allow us to generate random numbers. So in this video, let us try to use some of these functions a little bit, in particular the ones for file handling. So to briefly recap the new setup that we have, I'm using this package demo package that we created in the last video now. That means if you look at the contents of the current directory, they look as follows, right? We have this changelog file, which isn't strictly speaking necessary, but which was generated by Cabal init. We have this package demo Cabal file. That is rather important because it specifies that we are now, among other things, that we are depending on the base package that we've always already dependent on, but also on the random package and on the directory package that is in this package demo Cabal file. Right? Then we have hie.yaml file for telling the Haskell language server support for the editor that we want to build this particular project as a Cabal project, so to help it along. And then in the src directory, we have our mylib.hs, our actual source file, which is currently containing this. I've added a pragma again to give us warnings, which currently leads to the fact that we get warnings for these two imports because we do not actually need them yet. So I could comment these two out for the time being. And then we are now using Cabal REPL rather than GHCI to actually give us an environment in which we can try out the code that we are writing. So let us start by using a few functions from system.directory. And so I'll load this again, and I'll accept the warning for the time being because I don't have any code in this module that is actually using the stuff, but I do want to use these functions in GHCI to start with. And so one operation that we can be using is get directory contents. And get directory contents is taking a file path. Remember that a file path was just a synonym for a string. So basically the file path specifying a directory, and then we get a list of file paths of files that are in that directory back, but we of course do not get back that list directly. We get an IO action for such a list of file paths back. So let us try this out. And we can look at get directory contents for the current directory, which we can just refer to by using a dot. And then I'll see something that is quite similar to what I've just been showing from the operating system command line. We can see that we have these files, hie.yaml, changelog, md, src, package demo, Cabal, and this new style in the directory. By the way, this new style I did not mention before is a directory that is created by Cabal the moment you invoke some Cabal commands to store some metadata and build results and so on and so forth. And we also get dot for the current directory and dot dot for the parent directory shown here. And in fact, I mean, I could just look at what is the contents of this new style to just, for the fun of it, we can have a look at that as well. So if we execute this action, then we see that this new style directory contains other things such as some cache, some temporary files, a package database, and some build results. This is actually a subdirectory again, which contains all sorts of stuff. And you can see that get directory contents is giving us back both files and directories. So we could want to write a function that only gives us back the files in the current directory. So I can try to do that. Files in current directory. So that's actually not even a function at all. That is just an IO action that gives us back a list of file paths. And to start with, this is using get directory contents dot. But this is giving us back too much because it contains not just the proper files, but also directories. I want to get rid of the directories. So I would have to go through the resulting list of file names and check whether they are in fact regular files or whether they are directories. And that is something where we can use this filter m function for that we have been discussing previously. Right? Remember, filter m had the type a to io bool list of a to io of list of a, or it had actually a more general type than that, but this is the type that we are interested in using it. And this filter m function, I could redefine this here again, but I can also now just import it from control.monad. And there it has a more general type, as we have seen, but we can think of it as having the type that I've just given. And now, because I want to do multiple things in sequence, and filter m is again something that produces an IO action, because in order to check whether these file names are in fact regular files or are directories, right, I am going to have to do more file system accesses. Right? So I can just use do notation again, and then here I get my candidates, or I can actually just call it contents, perhaps. And now, remember always the types, get directory contents as the type file path to IO of list of file paths. So here to the right of the arrow, we have an IO action that returns a list of file paths. So contents has type list of file paths, right? If we pick up the result of the IO action, then we have just a list of file paths now. And we can use this list as an input to filter m. So here we want to call filter m on contents. And that filter m turns a list, I can actually look here, down here, right? Turns a list of file paths into an IO of a list of file paths. So this, in the end, has exactly the right result type for what we want to produce here. The only thing I have to still fill in here in my whole is a function of type file path, so that gets a single file path, and then produces an IO bool, so is allowed to do some IO, but has to say yes or no. And that is exactly the right type for the function that checks whether something is a file. So there is this does file exist function that, given a file path, checks whether it exists and is a proper file. So we can actually look at the documentation for does file exist. So it says it checks whether the file exists and is not a directory. Right, so that is exactly what we are interested in here. Okay, and now the whole thing type checks. And if I reload and I look at files in current directory, I get only hie.yaml, changelog.md, and package demo cabal. Let's compare this once again with the plain output of get directory contents dot. So here we got the current directory, which is a directory. We got src, which is a directory. We got the parent directory, which is a directory, and we got this new style, which is a directory. All of these are now removed from the list. Okay, so this is a way that we can combine functions that we've already seen and also put filter m to a reasonable use finally, right? Another thing that we could ask is, for the files that are in the current directory, what are their file sizes, right? So there is a function get file size, which takes a file path and returns an IO integer. Again, we can ask for a documentation, and it actually gives us back the size of a file in bytes. So this is an annotation you sometimes see in documentation strings that says that it's a function that has been added to the library at some point, and then it shows the version number of the library since when the function is around. And we can just try that on a file. So get file size hie.yaml, for example, gives us back 50, right? So again, the type of this is IO integer. If I type this into GHCI, the action is executed, and we get back the size of hie.yaml, which is 50. So we can look for the plausibility also. We can, just for the fun of it, we can also check what are the actual contents and what are the length of those contents, to just put that in relation. So perhaps this is another moment to introduce a little bit of extra syntax that we have for convenience in GHCI. So we have this possibility of saying read file of hie.yaml, of course, that reads the file and gets back the contents as a string. But if we now want to continue using the contents, right, because read file is an IO action, it would be nice if we could give it a name. And indeed, we can use this left arrow syntax from do notation also in GHCI. So we can also say something like, or let's just call it string left arrow read file hie.yaml. And then we don't get the output printed. Instead, we have string available as a string. And if I evaluate string now, it's just a plain string, and that contains exactly the file contents. And now I can do things like computing the length of this string, and we see that it is exactly 50, which is what we would have expected after the output of get file size. Okay. Now, if we want to get the file sizes for all the files, so if, for example, we want file sizes in current directory, and we want perhaps something like a list of pairs of file paths and integers, where the integers denote the size. What can we do? We can start by getting the files in the current directory. Right. And then we have to do something for every file. But the operation that we need to perform for every file is again something, namely get file size, that delivers an IO action. And we had been seeing this before, like if this is a bit like mapping get file size over the list of directories, but that gives us a list of IO actions. So we have to call the sequence function afterwards, which turns the list of IO actions into an IO of a list again, which is what we want here. So, and this combination of just sequencing and mapping is also available as mapm, right? So this is mapm. It's easy to define ourselves if we have sequence already. It's the composition of sequence and map. Actually, I need to pick up the argument of sequence and mapf. That is exactly what mapm does. But in fact, I don't need to define mapm myself because it is also defined in control monad. And in fact, if I were to define it myself here, I would get a name clash. So I can just use this now. So this is a good way to put mapm into action. So here I want to call mapm on the files in the current directory. And then if I look at the whole again, what I now have to provide is a function that goes from file path to IO of a pair of file path and integer. And this is, like, I mean, if I would be happy to just have the file sizes, it would be really easy. Right? Then the type of this would be just file path to IO integer, and I could directly fill in get file size here. But if I do this and I call it, then I just get these file sizes. I don't know which file has which size, so I would really like to have the pair of the file path and the integer here. And then this function here is incorrect, in type incorrect. All right, so we need to do something more than just that, but probably something involving get file size. Right, so let's just see again. We have to write a function that goes from file path to IO of a pair of a file path and an integer. So let's just use a lambda abstraction, and we get the file path. Right. And then here I just have to write an IO action that produces a file path and an integer. And now I have multiple options. So I can use do notation again. I could define a helper function, or I could reuse stuff that I already have. Right. I could realize that in terms of the effects, what I want to do is exactly still get file size. And then the only thing that I want to do to the result of get file size is that I want to pair the resulting integer in the IO action up with the file path. So I can use fmap. Right? So use fmap with something on get file size. On get file size of fp. And then I'm missing a parenthesis. Okay, so now it type checks except for the whole, and I still have to write this function that takes an integer to a file path and an integer, but here I really just want to pair the resulting integer up with the file path. So I can actually partially apply the pair to the first component. That is one option. So use the pair constructor with the first component. Actually, perhaps as a little aside, if you want to partially apply a tuple, right? A tuple is a little bit like a binary operator, but a binary operator with a rather special syntax in this case, a pairing constructor. So perhaps you think we could just write this, where we put the first component into the pair and then write a comma and leave the second component empty. And indeed, we can basically do this, but we get an error message now which says illegal tuple section, use tuple sections. And what this means is that this is actually available as a syntactic construct, but it is a language extension again. It's not in standard Haskell. We have to enable a language extension if we want to do it. And we know by now how to enable language extensions. We have to go to the top of the file, write language, and then use the name of the language extensions, write tuple sections, and then I can actually write it like this. Now, what I'm doing here again, let's look at this line 17. Right? We are starting out with the files in the current directory. We're doing something on every file, but the operation we're performing on every file is a side affecting operation. That's why we're using mapm and not plain map, right? Because we do all these things in sequence and we explicitly sequence them. And then for every file in the current directory, right, fp, we obtain its file size, and that is again an I/O action, and then we are modifying the result of that I/O action by pairing it up with the original file path. And again, I could also use this dollar operator rather than fmap, which sometimes looks a bit more beautiful and allows us to get rid of one pair of parentheses. So that is yet another option. And if I execute the action now, I do get that hie.yaml is 50 bytes large and changelog.md is 150 bytes large and packagedemo.cabal is 395 bytes large. And actually, if I go to another directory, which I can actually do by just putting a shell command into GHCI, so this :bang allows me to escape to the shell and actually execute a shell command. So I could change my working directory to src. I could invoke the same function again. Oh, actually, apparently it does not do this in such a way that, interesting. So apparently apparently this is not done in, so perhaps I should do it using Haskell. So I have to actually look, set current directory, I think is the function that allows to do this from Haskell. So we can do set current directory src to descend into the source directory, and then let's call file sizes and current directory again. And now we are in this src directory, which only contains mylib.hs. And that is a substantially larger file because it's the file that I'm just editing here. And in fact, if I make this larger, for example, by adding like extra new lines here, and then reload, actually I wouldn't even have had to reload in this case because I'm calling the old code, but on a changed operating system state, the reload actually resets the source, the current directory. So I need to set the current directory again and then call this again. And now I get 463, and before I had 461. Okay, so let's go back to the default. All right, so this is all nice and well, and there are plenty of operations available. We can not possibly go through them all, but also this is not really about Haskell. This is more about learning about libraries, right? So you have the skills now to understand these functions and understand their type signatures and understand how to use them. So you can basically just go through these libraries and understand their functionality itself. There is, however, something that I have been carefully avoiding to trigger so far, and that is what happens if I do something that doesn't really make sense, such as trying to, for example, read a file that doesn't even exist. Right? We haven't been doing that. So we have been doing something like, so if I'm reloading and now I think I'm in the normal directory again, so if I read file hie.yaml, I get the contents of that file. But what if I use a file here that doesn't actually exist? What do I get? The fact is I get an exception. The program crashes. All right. Now, I said in the past always that crashes are really, really bad, right? And that we should avoid partial functions and functions that are crashing. And I stand by that. But the situation here is a little bit different because we have to understand when the program is crashing. So if we look at the read file type again, then the promise that the type signature is giving us is that it takes a file path and it produces an I/O action that ultimately returns a string. And the function readFile satisfies this promise that the type signature gives us. It does take a file path, in our case test.txt, and it gives us successfully an I/O action. The production of the I/O action is not what fails, and in fact evaluating the I/O action does not trigger any effects, as we have been seeing that before. It just evaluates the plan for doing I/O, so to speak, and that is perfectly fine. The plan is not the thing that crashes here. The crash happens during execution of the actual side effects. And it's working in our favor now that execution of the side effects is much more clearly defined, in which order it happens and whether it happens, and so on and so forth, right? So we have an exact sequencing of the plan within the I/O action, and when we start executing it, it is exactly clear which effects happen in which order and at which time. And if there is a crash happening during execution, it therefore is rather clear when and where we can deal with that, and how we can catch it and how we can react to that. One of the problems of normal exceptions that arise in pure code that does not involve I/O action, is exactly that it is so difficult to react to them, because we don't exactly know when is this function even evaluated, right? But now we are in a different situation, and we do know relatively precisely when something is being executed. Okay, and the other point to keep in mind is simply that there are a whole lot of things that can go actually wrong, even though we have not been encountering them, right? But if we execute readFile, one option is that the file does not exist, so that we have what we have seen here. But another option is that the file does exist, but we do not have permissions to read it. So that would be a different kind of error, right? Yet another possibility is that the file does exist and we do have permission to read it, but there is a disk I/O error for some reason, so we cannot access its contents, and trying to read the file content somehow makes the disk crash, and we still cannot come up with a result. ReadFile perhaps cannot trigger it, but other things that can be triggered are things like the disk being full, right, or a network connection being lost, or all sorts of things in the context of I/O actions can in general go wrong. And now, of course, you could still say, and some people would actually advocate this, that the correct type, the proper type of readFile should actually be not I/O string, but it should be something like I/O maybe string, or I/O either error message string. And there are some libraries that are designed according to such an approach, where actually even within the I/O world, functions are explicit about all the errors that they can trigger. But there are also libraries, and in particular the ones that are probably the most widely used ones at the moment, that actually in this context do make use of exceptions. And that means that we briefly have to talk about how we can properly react to exceptions. I don't want to spend too much time on this, but let's just briefly check how we can deal with exceptions. And the answer is perhaps surprisingly simple. If we are in a world of I/O actions where we do have relatively fine-grained control, we can just deal with exceptions in much the same way as we can do in other languages. We can try to catch them. So in many languages, you have something like try-catch constructs, where you can run a certain amount of code and basically guard it in such a way that if within that piece of code an exception is being triggered, then you can call a handler. Then you intercept the execution and you call a handler. The handler perhaps can query information about the exact nature of the exception that has been caught and can react to that. And so if I import system.io.error, I have a function called catch.io.error. I have to reload. And this is just a warning at the moment because system.io error is imported, but I'm not actually using anything from it. So I have catch.io error here. And catch.io error takes two arguments. It takes an IO action as an argument, and this is the IO action that I in principle want to run, right? And it has a result of some type A. And now if during this IO action, during the effects of this IO action, during the execution of the effects of this IO action, an error is being triggered, an exception is being triggered, then the handler here is called. This is the second argument, is the handler. And the second argument gets access to some information about what exactly the IO error is, right? So we can, for example, check whether this is an error message that says that the file does not exist, or whether it's an error message that says whether it's a permission problem, and so on and so forth, right? And then we can recover, right? So given this IO error, we can say what we want to do. And we can recover in multiple different ways. So we can perhaps try to wait a bit and then restart the original operation, or we could try to produce some different kind of result, some default result. Or we could also, if we really say we can't handle the error situation after all, we could re-trigger the exception. And if an exception is triggered in this part, then it is propagated from the whole thing. You can have another catch.io error around this. All right, so to see how we can deal with this, let's look again at the situation here where we called read file with a file name that does not exist. All right, so if we wrap this up in catch.io error, right, then at this point here, I can write a handler. And now I can write a relatively simple handler that basically just ignores the error and just returns an empty string. That is one option. So here, this is like replacing failure with a default value. So we're just assuming that if the file that we want to read does not exist, then rather than the string that is contained in the file, we're going to return the empty string. And we can see that if we execute this, it actually successfully intercepts the exception and handles it and returns the empty string. And if we call this with a file name that does exist, like hie.yaml, right, then no exception is triggered and we get the file contents. Of course, we don't have to use a default value. We can also use things like the maybe type. If we say the whole computation now should not return be an IO string, but an IO of maybe string, we can say that in the case that there is an error, we just want to return nothing. But now we have a type error because our handler returns a maybe type, but the action that we're executing normally returns something that is of type string. But catch.io error says that the action that we want to perform normally and our handler must return the same type. So we have to make this action here, read file hie.yaml, we have to make that return a maybe thing as well. But we can do so by just modifying the result of read file in such a way that we wrap it in just. And again, this is an application of fmap. Right? We have read file hie.yaml, which is an IO string, and we just want to operate on the result of reading the file by applying just to it, and we can do that using fmap. So this is another option Now, in the successful case, we get just and then the string with the file contents. And in the unsuccessful case, test.txt, we get nothing. If we want to react or somehow take into account the actual nature of the error, right, we have to look a little bit closer at this catch IO error situation and at the IO error type. So perhaps the best way to do this is to look at package once more and to actually go to the base package again, because system.io.error is actually part of the base package, not of any of the other packages that we have been interacting with. And then we see that there are a couple of functions here, but in particular there are functions that allow us to classify IO errors. So IO error is not really a data type that we can pattern match on. It's essentially an abstract type, but we do have all sorts of functions that we can use in order to check whether it is representing a particular kind of error. So we see in particular there is this is does not exist error, which is exactly the situation that we are in. So we could use that here. And in order to check whether we actually have an is does not exist error, right? So we can check like if is does not exist error, then return nothing. And otherwise, right, we could just rethrow the exception. Right? We don't want to handle any other kind of error here. If it's any other kind of error, we just want to rethrow the exception. But for that, we have to have a way to rethrow the exception. And that function is called throw.io, but it unfortunately, I think, is not contained in the same it's not contained in the same module. It's contained in control.exception. Yes. So I want to say throw.io ERR here, but I'm not having that function available. So I think for this I have to import control exception. And then I'm getting another warning because I'm not in my source file using anything of control exception. But here, this now works. And because the error that I'm catching is actually the is does not exist error, right? Because that is actually the situation that if I'm using this with a file that does not exist, it still returns nothing. It does not propagate the exception. Right? So I could try to provoke a different error now, but I can also just check for a different kind of error here to demonstrate this. So is permission error. So I could check, like, say I want to handle only permission errors. And if I try to handle only permission errors, then you see it would still not get caught, and the exception is rethrown because I'm throwing it again here at this point. I think this is basically all I want to say about exceptions at this point, right? So, but to recap once more, the reason why exceptions in the world of IO actions are less problematic in general is because it's very clear that we can catch them, right? Because if we have this argument here, this is an IO action, and we can very clearly state that if something happens during the execution of effects in this IO action, during this IO action, then we're going to catch it. Right? This is very different from trying to catch exceptions in pure code, because we don't have a clear handle as to when something is being evaluated. If we wrap a pure computation, if we had some sort of catch function in general, and we wrap some pure computation here, something like, well, let's rather use like the head of the empty list, right? It's not clear when the head of the empty list is going to be evaluated or whether this is being used. It depends on the context of this whole catch block in a situation like this, whether this is even triggered, right? Because otherwise this might never get evaluated. And it's even more problematic if the head of the empty list is buried somewhere deeper inside of this expression, like as a sub-expression somewhere. It's relatively unclear whether it'll ever be called, right? And then at which point we would have to trigger the handler. So that makes it much different in flavor. Okay, I think that concludes what we currently want to say about using various other I/O actions from libraries and dealing with exceptions.